one means the empty word is a palindrome. That A, B, and C, just the single tokens or symbols are palindromes. And then this recursive means that if B is a palindrome, then A, P, A is one, B, is one. So this grammar would describe the language of palindromes over the alphabet ABC. Lines are called production. So you can see them as rewriting the left hand matches, then can be replaced by the right hand side. And there are terminals and non-terminals, the symbols here on the right hand side. So our symbols itself are terminals, are called terminals, and then you can also have non-terminals that are not in the alphabet and can't appear in the final word. So in this example, the capital P is the only non-terminal. Right. And one can use that to generate words. So starting from non-terminal, we can apply production successfully until we reach the word of terminals. For example, we could start with P and then use this rule to get here, then use this rule to rewrite the at the center in CPC, use the same rule again to rewrite it like this, and finally use this rule to rewrite this P to a D, and then you have only terminals, so A, C, C, B, C, C, A would be a valid palindrome. And such a sequence is called a derivation. And all words that can be derived from a non-terminal are in the language generated by the non-terminal, and that non-terminal is called the start symbol of the language. So in our example, the capital P would be the start symbol of the language of palindromes. Right. And in the grammars that we consider, they are restricted. So the left-hand side of a production is always a single non-terminal. And grammars like that are called context-free. And I think programming languages are sometimes not context-free, but some are. So that's like an important subset of languages. Okay. And not all languages can be generated by a grammar, and even fewer languages can be generated by a context-free grammar. But languages that can be generated by a context-free grammar are called context-free languages. And context-free languages are relatively easy to deal with algorithmically, and therefore most programming languages have a context-free syntax. And also it may not be unique, so multiple grammars may generate the same language. So let's see. Another example, a very simple language of single digits. So a digit can be one of the symbols from 0 to 9. And then there are some rules to basically write these productions in more compact form. So if you have several productions for the same non-terminal, like in our case the dig, then they can be joined with a vertical bar, like so. And for example, we could, if we now have simple single digit, we would like sequences of digits. So we could define it like this. So a sequence of digits is either the empty word, or it's a digit followed recursively by a sequence of digits. And I mean, with this, we could have a 0 in the beginning, because I mean, 0 is also a digit. So here's a derivation for 007, which is in dig. So you apply the right rule sufficiently many times, like 3 times. And then you apply the first rule here. So the last digs is now epsilon. So you have 3 digits, and then you can apply, I mean, the appropriate rules here to derive 007. And there's a abbreviation for this, because that's very common that you want 0 or more occurrences of something, and that's just put a star. So one would write this rule here alternatively just as dig star, so star means 0 or more. Maybe some of you have worked with regular expressions. I mean, that's also it's the same thing. I think it's called the clean star after some mathematician or computer scientist. It was called clean with K and double E. So if we want like only natural numbers or sequences that start with non-zero digit, we could define a new non-terminal that doesn't have the 0. And then we could, for example, define a natural number is either a single 0 or it's a non-zero digit followed by 0 or more digits. So this would be a proper definition of the syntax of the language of natural numbers. Right. And if we wanted to do integers, we could define sign as either plus or minus, and then integer could be sign nut or nut. But this, for example, would also allow something like plus 5. So we could also alternatively just have minus nut or nut. And even maybe forbid the 0, minus 0, I mean. But this would allow minus 0 as well. Okay, and the sign is optional. So this second rule says you can have sign nut or nut. And there's also an abbreviation for that, which you maybe also know from regular expressions. You can do that so that gets abbreviated as a question mark. So a shorter way to write the second rule would be sign question mark nut. So that's optional. Right. So far that's pure theory. And now we'll see how that can be connected to Haskell. But other questions at this point? Maybe you have seen those things before? Yes? Empty word. Empty.
At the end of a string, denotes that there is end of what?
No, end of file is a different thing. So it denotes the empty word. And you also had a question?
Yeah, it's more general. So the concept itself is trying to create a representation, a way of passing.
This is basically. It's to formally define like syntactic rules for some language. I don't know. I can't think of. Maybe I try to think of a good example where like a commonly known that has like where it's defined like that. Do you know any website where?
Or you can see like the rules
of something of maybe not JavaScript but JSON or something.
Right. No, I'm not aware of the rules, but JSON has this spec. What's it called? But there's a document that specifies how the rules of how JSON should work, and it's like this. Like denotes how the language should work. And then when you create the actual interpreter of JSON, you create based on those rules.
But not every language has it formally specified. But several times in my life I've encountered, some description of something, where they do formally specify it like
JSON
that.
Has like a couple, so it's been updated a couple of times. So yeah. You can see that, and you can actually just based on that implement your own JSON encoder.
So it's like defining a specification.
Yes, it's like a specification for a specific language. It could be a programming language, but it doesn't necessarily have to have anything to do with programming. Basically, syntactically, just syntax. How does a well-formed whatever JSON expression look like? So you could say it can be, you could say JSON is either whatever number, and then of course you have to specify, and then, string, or a list, again, of JSON objects, and so on. I don't know whether JSON does have a formal grammar.
Yes, I think you can do that.
My browser always needs some time to get started. Just a second. I think maybe I didn't. There we go. I'm not sure. I mean, I haven't tried that formal grammar or something.
Formal specification.
Oh. Right. That's basically one, right?
Yes. Keyword, user schema. That's it? No.
I think this is about
Now, if you go
JSON
back to
schema.
the second link, there's an explanation, like to the Google
Yes.
search.
Uh-huh.
In the second wire formal specification, maybe.
But I think JSON schema is, that's something else, right?
Yes, but if you go up,
Sorry.
there's the same wire formal specification, and maybe
There's an example.
leads to.
But this is, I think this is like JSON schema. That's for specific, I mean, to
What is the grammar for JSON?
yeah, I think this is something else.
JSON.org.
Maybe here?
That sounds.
That sounds like authoritative. Yeah, here. This is another way to do this. I mean, these diagrams are another way to do this, what I did in production, with these production rules. So that's a graphical way. So here they have formally specified exactly what a JSON thing can be. And basically have said what is white space, what's a number, what's an object, and so on. And you could transform these diagrams into this form that I had on the slides. So this is formally tells you exactly which documents are valid JSON documents.
So someone implements this as a parser.
You could use it to write a parser, yes. Or
But someone trying to do JSON, that JSON will be checked against the parser.
yes,
From these rules, right?
yes. I mean, yes.
And the whole idea is that this is like the source of truth, and then everyone that wants to interact with JSON files needs to respect these rules, and it will always work. That like the idea is that if you respect the rules, it will always work.
So I mean, this here, for example, says an array always starts with opening square brackets, and then either there can be white space and a closing square bracket, or there can be a value and closing, or there can be a value and a comma and another value and so on. And you could write that, I mean, this diagram, you could write it in these production forms. And of course, then so array would be a non-terminal, white space would be a non-terminal, value would be a non-terminal, but the circles here are terminals, so the square bracket and the comma. And then these non-terminals, they must be defined elsewhere, further down probably, like white space here. I mean, here they say what white space is. It can either be the empty word, or a space, or a line feed, or a carriage return, or a horizontal tab, or several of those. And yes, so I mean, this is a different way of basically writing down the same idea. Yes, and it gives you an advantage. I mean, it's formal, so it can basically be checked by a computer. So once you have a description like that, you could write a tool where you give it a document and it says that's valid JSON or not. It follows this or it doesn't. And of course, it's also a form of documentation. If you are not sure how you can format your JSON document or whatever, you in principle can check here and see whether it's, for example, allowed after the opening bracket of a JSON array to have like 2 spaces. And if you are not sure, then this will tell you that it is indeed. Although I'm not so sure. It shouldn't. It's not allowed.
Yeah.
Right. So I wasn't sure. I thought it might be allowed. But according to this, it's not. Because if you have a white space, you are done. So, yes. Okay, interesting. So it seems that's not allowed. Of course, maybe that like existing parsers are more lenient sometimes. But according to the specification, array that's not the empty array must immediately after the opening brackets must have a value. Nice. Now we know. Okay, anyway, so that's like grammars. And I mean, parser, you normally want to parse something that has a grammar. So first you need to understand what the rules are of the thing that you are parsing. So yes, and now in the lecture we will see how basically given a grammar, you can write a parser for that grammar, what that even means. Are there other questions?
The syntax for this, it seems like syntax the same as the syntax for that, but the other way, but
Sorry, the syntax is the same as syntax for what?
types, like when you define types, you define
Ah,
structures.
that's a very good question. We come to that now, basically how it relates to Haskell types, because there is a close relation. Very good. Right. And first, briefly, let's talk about parse trees. So let's take this example grammar. So the non-terminal is S, capital S, and S can either be a single letter A, or it can be two S's. Then if we look at this word AAA, there are at least the following derivations. So we can start applying the second rule, SS, then apply the first rule to the first S to turn it into AS, apply the second rule again, apply the first rule here, and then we go to, and again, to the last one. Or we can, instead applying the first rule here to the first S, we can first apply it to the second S, then, and so on. So they are like, I mean, this means, I mean, that you, by definition, if you have a derivation, the word is in the grammar, so AAA is in this grammar, but that doesn't necessarily mean that there's only one way to derive it. And one can visualize this like so. And something like this is called a parse tree. So each time you apply one of the rules, you basically go down one level in a tree. And at the bottom level, you only have terminals. And we see these trees are different. I mean, it's not the same trees, but the bottom level is the same. So in this case, there are several, and something like that is called a parse tree. And it's not unique, but so this is called ambiguity. So if every word in the language has only one a unique parse tree, it's called unambiguous. And if it's not the case, then the grammar is called ambiguous. So this one, as we saw, is an example for an ambiguous one. And the meaning of a language, whatever that means, meaning, often will be defined via parse trees. We will see examples of that later, which means that if you have an ambiguous grammar, because then for the same word there can be different parse trees, there are like different meanings. So that sounds like dubious. And so like normally grammars should be unambiguous, ideally, because otherwise you have this ambiguity. And right, and what I said, so parsing problem is if you have a grammar and a language generated by it, then the parsing problem is to decide whether a given word is in the language. And if it is, you would also normally like a parse tree for it, basically a proof that why you come to the conclusion it's in the language. So basically the problem is given an arbitrary word, either produce a parse tree for it or say it's not in the language. And right, and now let's look at this example. So another language with two non-terminals, S and D. D can either be 0 or 1, and S can be D plus S or D. And as an example word, we have 1 plus 0 plus 1, and we can have a parse tree like this. And now we come to what that has to do with types, how we best represent such a tree in Haskell. And the idea is that the non-terminals will correspond to data types, and if we have like for a given non-terminal we have several productions, then that will correspond to several constructors in the data type. And right, so I mean this corresponds. So if we look at this again on the left, so S and D would correspond to data types. Now maybe I can like actually do this in parallel, I mean. let me maybe just copy this here. So we have S is, what was it, D plus S, S or D, and D is 0 or 1. So that's the grammar. And now the idea how this corresponds to Haskell would, as I said, the non-terminals are data types. So we have two data types, S and D. And now each production for that data type corresponds to a constructor. So for D, okay, let's start for D. So we have 2. So we can call that whatever. I mean, that's not given by the grammar. We have to pick something. Let's call it 0 or 1. And the S, we have this, let's call it plus the constructor. And another correspondence is that in these production rules, there can be non-terminals or terminals. So the non-terminals on the right-hand side of the arrow will be arguments to our constructors. So here for D, there are only terminals, so we end up with constructors without arguments. But here, in the first case, there are two non-terminal arguments, D and S, so they will be constructor arguments. So let's, of the obvious type, so of D and of S. So we have plus DS, that's the first rule. And the second rule, there's one non-terminal here, so it will be a constructor with one argument. And we can call it whatever digit, D. So that would be the correspondence between such rules and Haskell data types. So again, each non-terminal corresponds to a data type. Each production for that non-terminal corresponds to a constructor. And each non-terminal in a production corresponds to an argument of that constructor. So that's basically a one-to-one correspondence, more or less, between Haskell data types and these productions. So far clear how I get from the one to the other? Okay. Let's see. And basically that's more or less equivalent. I mean, of course, I had to invent names for the constructors that are not in these grammar rules. But apart from that, it's more or less the same information. And so, yeah, the left one is called concrete syntax, and the right one is called abstract syntax. And now parse trees correspond to values of that type. So we had a parse tree where the root was an S. So now this parse tree corresponds to a value of the type S that I defined. So the first step here was that I applied this left rule here, which is the first constructor here. So the top constructor of that value is plus. And then I have the D and the S. So the D, the second constructor was used. So it's 1, because this is 1. And now on the right child here, the S, I used this rule again. So it's again plus, and then the 0. And now for this S, I use the second rule in this tree here. So it's the second constructor, it's the digit constructor, which is then here. And finally this D1, so 1. Okay, so this value 1-to-1 reflects the parse tree. So there's like a 1-to-1 correspondence between values of these data types and parse trees. Okay? Right, so I could, I mean, I would have this value if I wanted to. I'm not sure whether I wanted. Example 1, type S. What was it? Plus.
Plus 1.
Uh-huh.
And then plus. And then 0.
I'm sorry?
0.
Uh-huh.
And then digit
digit 1, right?
1.
I think so. Was it like this? Yeah, okay. I could yeah, well, that's that. So that's like one connection to Haskell. So these, one can understand these grammars as data types, basically. And the parsing problem then becomes to, given a string of symbols, parse that as a value of this data type. Right. And then there are so-called semantic functions. So, this is just an abstract thing. It's a parse tree. And that doesn't have any, semantics means meaning. And a priori, something like this doesn't mean anything. It's just a representation of the syntax. But you can give it meaning by writing so-called semantic function, and that's a function from this data type to whatever. So, and there is not just one. There can be different semantics for a given type. So in this example, there are at least two things we can reasonably do. One is to basically get the word back as string representation. And another one is to interpret it as an arithmetic expression and evaluate it. So just as an example, sorry, just want to check quickly whether there's any fishy stuff. No. And typically, if you have like several non-terminals, then you need to write this function for each of the non-terminals, and they are often mutually recursive. So let's try this. So let's do the print semantic function first. So we want print s from s to string. And typically, as I said, you have something like this then for all your non-terminals. So we will also have a print s from d to string, and often they are mutually recursive. And this is just standard design pattern for functions. So s has two constructors, so we have to consider two cases. So plus ds. Well, how would we print that? We would recursively print the d. Sorry, it's lowercase. Then we would have our plus symbol, and then we would recursively print the s. And the second constructor, digit d, where we would just call this print d on the d. And now for the d case, there are two constructors. Print d0 would just be the string 0, and print d1 just be the string 1. And we can try our semantic function on our example.
No, doesn't load. No modus loader.
Yeah, right. I made a mistake somewhere. Seems. Hang on. Let me just reload this. Let's see.
Oh, you're missing.
Oh, the argument. I'm missing the d. Okay. Okay, now it loads, and now it should be hopefully work. Right, so now if I use this example value, then I get the original string back. But there's another reasonable semantic, namely, this obviously is supposed to model like simple sums of zeros and ones. So I can also have a second semantic function eval for evaluate. So again, I need two versions, one for s and one for d. And again, I have the cases. So there is the plus case. Is it d and s? Yeah. plus ds, and I mean it's very mechanical in this case, so in this case I would eval d and add it to eval s applied to s, and in the digit case I would eval d, and here the obvious, so the semantic of 0, of course, is 0, and the semantic of 1 is 1. So I could do that, and if I didn't make a mistake again, I can apply eval s to our example and get 2, because 1 plus 0 plus 1 is 2. Right. So the point is that, I mean, syntax trees or parse trees don't have any meaning by itself. So if you, for example, take a programming language, then parsing is, I mean, if you like want to implement your own programming language, then normally the first step is to write a parser. So I mean, somebody gives you a text file with source code, and then you first parse it into which in that context is often called an abstract syntax tree of the language. But that tree doesn't have any meaning by itself. And then you would next write a compiler or an interpreter that takes that tree and does something programming related. And that, I mean, there can be several things. I mean, maybe you want a pretty printer or formatter for your programming language. That could be something like this print s, or you want whatever, an interpreter that actually executes it. Right, so that's like the difference between syntax and semantics. So parsing and grammars deal with syntax, like correct formal rules to, I mean, how text defines something in your, I mean, the right shape of things. But then to give it meaning, you basically that you can interpret that as a function from that thing, this abstract syntax tree, to somewhere. Can be a string representation, can be evaluate or whatever, or IO action. That's actually the little robot. Yes. Okay. Did this. Okay. So far, any questions before we go to how to parse? I mean, how to write a parser for this, for these things? Okay. Right. I mean, this is probably not very interesting until now. I mean, it's just interesting that, I mean, that there is this correspondence between, I mean, that was a thing long before Haskell, I think, these grammars, and that so closely corresponds to algebraic data types. It's interesting. Okay, and now we will talk about parsing. And there are various approaches to parsing. And I think the traditional approach is parser generators. I mean, if you have ever done, I don't know, if you ever in your life needed to create a parser, but I mean, the traditional approach is to have external programs. Let me first do the left thing. So that's the traditional one. So it's a bottom-up algorithm. It's complex theory. Normally, they are somewhat restricted for efficiency, so they only look ahead one character or so before they decide what to do next. They are very rigid. I mean, they can do what they can do, and you can't extend them. They are fast. And then the alternative approach is called parser combinators, which we will talk about today. And that's not, and I mean, yeah, okay, I think it comes later. But the external programs, so I mean, in C, there's this IOG and Lex, and that's quite famous. I mean, I personally never used it, but traditionally, if you wanted to write a parser for your own cool programming language, use something like IOG. So there's a C tool. It has a special syntax, and you can somehow in cryptic way define these grammars, and hopefully then it parses your grammar. But yeah. But parser combinators are just libraries, and it's top-down, very simple theory. In principle, you are not restricted by just looking ahead one character. You can, because it's like just a library, you can define your own abstractions, and it's fast enough. Maybe not as fast as these traditional tools, but for practical purposes, fast enough. And both approaches put certain constraints on the grammars. So they can't parse just out of the box all context-free grammars, for example. Because of this limited look ahead, for example, I mean, just as an example, if you want to write a parser for a programming language, and it has like 2 keywords that have the same first 2 characters. I don't know whether there is an example for that in an existing language that we know of. Whatever, if you had a programming language that has like a command print and a command prompt that both start with PR, then the left-hand side would already be in trouble, because in order to distinguish whether it's print or prompt, they have to go like look ahead 2, because they have to see the, I mean, what distinguishes the 2 keywords would be I and O. So, I mean, it's not strictly true because it would first tokenize, and it's a different story. But I mean, that's how you can think of this look ahead. So, so in order to distinguish whether now it will be print or prompt, they would look 2 characters ahead to see the I, O. And so these wouldn't be able to handle that. So they would have to commit to one of the 2 too early, and then maybe say it fails because they hoped it would be print, but it was prompt, and then they would say it doesn't pass, even though it would have passed if they had just looked ahead once more. That's this look ahead thing. So that means you must design your programming languages syntax with that in mind, that if you want to be able to parse it, I mean, you mustn't have something like that, like keywords that have a long prefix in common. And I think in actual programming languages that doesn't happen. I mean, I can't think of anything right now. This is not really important, it's just why it's called combinator. So that's a technical term from lambda calculus, which is like the formal system that is the foundation of Haskell. And parser combinators are like simple functions that, I mean, you start, parser combinators basically means you start with very simple parsers for very simple languages, and then you can combine them to build complex parsers for complex languages. So that's the idea of parser combinators. And then this is also not really important, just normally parsing is done traditionally in 2 steps, lexing and parsing. So first you do stuff like remove white space and comments, and organize your text into a so-called tokens, a stream of tokens. So then probably keywords I mean, you start with something, whatever, let x equals 42, and then the tokens, so let would just be a keyword, that would be 1 token, x would be a name, equals would be an operator, and then the 42 a number or something. So it rises the abstraction level a bit, so you don't have to worry about white space between the equal sign and the 42 anymore. So that is like a preprocessor for the parsing, and then you do the actual parsing once you have the tokens. So that's how it's traditionally done. So in C there are these tools. IOG, I think, is a parsing generator, but you also have this lex, which is a lexer. And often there are like different tools used for that, and so or flex. So in C it seems like a lexer is, for example, flex, and parser is IOG or Bison. And in Haskell there are also tools like this. So there's an LX, lexer, and happy parser. But when you use parser combinators, you have different options. So for example, you don't need lexing and parsing to distinguish the two at all. So you can just do everything in one phase. You can use the same parser combinator library for both phases, or you can mix and match. I mean, you can use like LX for lexing and then use a parser, or you can write your own lexer or whatever. But we will just, I mean, we won't talk about lexers and like these external tools, and just look at parser combinators, which are in principle, I mean, beautiful and powerful enough to do everything. Right. So the first question is, what should a parser be? So now we want to talk about parsers for a given language, and maybe I should like have different modules for the different versions. Yes. Yeah. So give me a second to maybe I have a. I'm very pedantic about alphabetical ordering. So we will now, like in a couple of steps, slowly go towards the actual type of what type a parser should have. So we will start slow and build up from there. Okay. I just want to check whether it still compiles. And
the word keyword.
I'm sorry?
The word keyword. You're missing the word after the module name.
Right. Thank you. Right. Okay, and our first attempt, let me just briefly check. Right. So the very first idea, so I said before, the parsing problem is you have a string and you are supposed to decide whether that string is a valid string in your language, whatever your language is, or not. So the first idea could be that a parser is simply a function from string to bool. Okay, so given a string, it decides yes or no. And with this simple definition, we can already define some parsers. So for example, we could have digit. Let me just check that I have the same names. Okay, so digit is a parser. And digit, if it's exactly one character, where that character is an element of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, then we say, yep, it's a digit, and otherwise, nope. Okay, so that would be a parser for digits. So now we could test it. So for example, the string 7, yes, our parser parses that, but like whatever an x is false, or also if I have more than one, it's also false, or the empty string is false. So yes. So that's looking promising. And another one we can define is end of file. And that's basically just null. So checking whether it's the empty string.
Null is a function that checks if a string is at least
Yes.
empty, not like other languages have no.
Yeah, and it's not the null pointer. It checks whether a list is empty. So end of file, the empty string is true, but end of file, anything else is false. Okay, so far so good. So we can define some simple parsers. But now, I mean, we want to combine. For example, once we had defined this digit example, we wanted to go to natural numbers. And then we said it's like 0 or more digits or 1 or more digits. But there's now, with this type, there is no way to use this digit parser to somehow turn it into a parser for digits. I mean, we could write one for digits by hand with this type. But what we want, of course, is to somehow use the digit parser to define a digits parser. But with this type, there is no way to combine parsers to more complicated parsers. So this type is not good enough. Right, so let's try again. And let me just copy this. If I could, but I can't because my editor doesn't allow that anymore. I should never have called it parsing parser because then autocomplete also doesn't work. Right. So let's call that 2. Let's add 2 here. And let's reload the window. Okay. Okay. So the next idea is, I mean, one of the problems for digits is, I mean, if we wanted to define digits in terms of digit, that we have no idea with the given string sorry. So now if it's the empty list, or sorry, the empty string, I cannot, maybe list, then it's not a digit. But if it's not the empty string, then if the first character is an element of 0 to 9, I don't just return true. Sorry. Instead now just, so it succeeded, it is a digit. I mean, I can pass a digit, and the remaining part of the input is the CS. And if it's, I mean, I could put it like that as well, but if the first character is not a digit, then I fail. Okay. And for this end of file, so if it's the empty string, it's true, so it succeeds, but there is no input left, so it's again the empty string, or like this. And otherwise, it's wrong. Okay? And we can try it, of course. So we can do a digit, well, with a single digit. So this tells me, yes, it's a digit, or it starts with a digit, and there's no remaining input. But I could now also do 1x by 4, whatever. And then it says, yes, it starts with a digit, and the remaining input is xu4. And I mean for end of file, so the empty string passes, and there is no remaining digit. But if I have something, it fails. Okay? And now we can actually combine parsers. So now we can look at something that first it should be a digit, and then there should be another digit. So I can, given two parsers, I can combine them to a parser that parses those two things in sequence. So I can call that combine. Combine. So given two parsers, produces a parser. Combine PQ. Applied to a string S. So now I'm in the maybe monad. So I first apply the first parser and get some remaining input, and then I apply the second parser to the remaining input. So if you remember what maybe means, so if the first parser fails, if this here already returns a nothing, then I don't even try the second, I just fail. But if the first parser succeeds, then this T will now be bound against the remaining input, and I apply the second parser to the remaining input and get the remaining, if it fails, it fails. But if that also succeeds, I get the remaining input of the second parser. And now I can do stuff like whatever digit, combine. I mean, I don't have to, I can, but yeah, why not? Combine digit of, for example, 1, 2, 3. Now, or parentheses. And it says yes, that's passes, so it starts with 2 digits, and the remaining input is 3. Or whatever, it can be anything, of course. But if it's like this, it fails, because it passes the first digit successfully, but then the second fails. So this is already cool, because it's now, I mean, it's called parser combinator, so we can combine already. You see? Okay, so at this point we can also, now we have digits, we can also define a parser for letters. So let me copy this. And instead of this, now of course I have something else, like A to Z, A to Z. So yeah. And now I can also do things like combine letter digit. Do I need this? Sure. So that also works. Right, and as you saw, I just copy-pasted this, and it was very similar. And we don't like copy-pasting, we like to abstract stuff. So there's a useful abstraction here. I mean, what's the idea? It must be, it's one character, basically, and that character must satisfy a certain predicate. So let me just see what it's called here, satisfy. So we can basically make this, abstract this and define something called satisfy that takes a predicate on characters and generates a parser. And let me copy paste one last time. So in this case, we don't care about the predicate, we fail anyway. But in this case, so we now replace this line with, we check the predicate, and if that succeeds, then it's just 6. And right. And now that we have that, we can define digit and letter using satisfy. So digit is just satisfy lm. I should have copied that. Maybe I should. And letter is just satisfy this. And that hopefully still works. So we can check it, whether the same example from before. Okay, fine. So that still seems to work. Right, so it's already, I mean, this version is already relatively useful. I mean, we can define our own abstractions and combine stuff, and I mean, you can already see how you can start building something like a library from this. And we can even define something, right, that we call character. Sorry. So the idea is that we have a parser for a specific character. So given a character, so that's a parser that will only succeed if it starts, or the word starts with a specific character. And this we now with the satisfy, we can simply define that as, must be C. So we can try that out as well. So if we do character X, X, whatever, and if it indeed starts with an X, then it succeeds, but if it starts with any other character, then it fails. Okay, so the satisfy is useful, and in particular we can build it to have this character, which you often want, because often you expect specific characters. Like in our example language, we had this plus. So for this one constructor, we were expecting specifically this plus. So we could use this char plus there. So this is
The open bracket in JSON.
yes, or the open bracket in JSON for terminals, where we know which ones. Right, and we can even now define our star. Which is called many in Haskell. So I could call it star, but I don't call it star because it's traditionally called many in Haskell. So it takes a parser to a parser. And I think that will clash with the prelude, but let's see. So what do we do if, let me just check how it does. Right. So many, P, S. So we apply the given parser to our string. And if that fails, remember many, the star also allows 0 occurrences. So the star should never fail, right? No matter what. So if the given string S doesn't start with a P, then we still succeed, but we just don't consume any input. So in that case, it's the empty word. So in that case, we return just S, the full string. And if it's just T, then we recursively apply many P to this T. Okay, and we can try this out. So for example, many digit. Now it might. Okay, works. So it consumes all the digits, but it would also work if I have fewer. Or even no digit, because the star also allows none. I mean, now I can already do relatively complicated. I mean, I could also do whatever, letter, combine, digit, x5, z0, k3, blah, blah, blah. Should also work. So yeah, I mean, you can build more interesting languages with those combinators already. Question?
So means the process have to be called in a specific order.
Yes. I mean, because order matters. The keyword for is different from rof. So I mean, the order matters normally with text, right? With syntax. You can't, yeah?
So like even possibly it would be HTML tags. How to call the process based on the first boolean checking Django bracket and the HTML and so on.
Right. Yes. I mean, in this, if I still have this open, I mean, for example, if you want to pass an array, you would first pass a square bracket, and then you would, I mean, this we don't know what you would do here, because now there are two options. But you would, for example, then pass white space, and then you would pass a closing bracket. So we would combine this char opening bracket with a to be defined parser for white space, and then combine that with a char closing bracket, for example. And then it would check that it must start with an opening bracket, then there must be white space, and then there must be a closing bracket in that order.
The whole thing to be valid.
Yes.
It has to pass the whole.
Yes. I mean, it's only valid, it's only invalid, if we ignore like this stuff here, the interesting one, if we only look at the first line, I mean, valid array must have an opening bracket, white space, closing bracket in that order, and all three must be there. Other questions? Okay, sorry. So that's cool. I showed you an example. Right. Many letter combine R. Right. But now let's look at this example. So we have, for example, many letter combine character A. And if we apply that to this, it fails, even though it should pass. I mean, because there are 0 or more letters and then there is an A, right? But what we have now, it basically is too greedy. The many basically only stops here at the 7, and then the A is gone, and so the second one, the character A, will fail. I mean, it should only consume the many letter should only take the first 3 so that the second succeeds. But there's no way for it at the moment to do that, because it always, I mean, there's only one, and it's always greedily, the many only always greedily takes as much as it can. So then we have already consumed BC, I mean, everything until here, and then when we get to passing the A, we fail, because then there's the 7. So that means it's still not perfect. I mean, we could do quite cool stuff, but we can't do that yet. And the problem is, I mean, it basically commits to one solution, even if they are, I mean, for the many, I mean, if we forget about the combined stuff, if we do this, then it just gives us, I mean, it passes all the letters. But, I mean, it would also be allowed to pass nothing or 1 letter or 2 or 3. But it only gives us this one solution. It doesn't consider the other possibilities that would also be legal for the clean star. So the problem is that we only return basically one possible way to pass it, even if there are several. In this case, it would also be okay to stop after the first letter, or even not consume anything, or stop after the first or the second. But in our current implementation, it always does everything. It only gives us one solution, basically. I don't know, at some point we should have a break, but maybe I do one more. Or? Right, so let's create version 3.
What's next?
A list, I think. Okay. Okay, must just.
Yes.
You said that a semantic function gives meaning
Mm-hmm.
to your language or your style. Language. So the difference between a semantic, between the parser and now giving it meaning.
Yeah.
What do you mean by giving it meaning? Because
Well, So if you have a Haskell file like this, but you don't have the actual compiler to run it and create like real, like an actual like effect, this has no meaning. This is just a bunch of strings in a file. So the actual text has no meaning. You can build a syntax tree out of it. You can build the actual syntax tree for this. But if you don't run any computation, so you don't produce a result based on that syntax tree, it has no meaning. That's the difference with the parser. You create the syntax tree, and with the evaluator, you like perform some actions based on that syntax tree.
Yes, it's the distinction between syntax and semantics. I mean, that's also like in linguistics or something. I mean, you can have, I mean, a sentence, you can analyze a sentence into whatever object, predicate, subject, and so on, but that doesn't give it meaning. I mean, there's something else. I mean, you have the formal, I mean, you can take an English sentence and like parse it into whatever particles and word types and clauses and so on. But that's only like what people call syntax, like it's meaningless. It's just formal. But then to actually give the sentence meaning, you need semantics, and that's something else. And it's the same here. I mean, if you have an expression like 3 plus 4, I mean, that's just 3 symbols, or 3 plus 3, 4. But to somehow fill this with that, what you mean by this is like it's 7. I mean, this step corresponds to a function from this thing, this tree, to an integer. But it's not the only possibility. It's obviously the one most people will think of. But another function could be to just take this tree and print it, or whatever, compile it to some assembly. Or
Makes sense?
Right. So the problem is somehow that we always, if we succeed, we don't consider all possible options. Let me just check whether So the next refinement is, and the problem is maybe something, it's either 0 or nothing, right? Either it fails or it succeeds, but then it only has this one option. So the idea is maybe it's basically a list that's either empty or one element. So the next idea is to instead of the maybe, give all possible solutions. So all possible unconsumed inputs. Now, of course, stuff fails again, but luckily not too much. So let's see. So the empty string should fail, and failing now corresponds to just the empty list. So here as well. And this corresponds to singleton list. So in this case, there's only one. And the nice thing is that now that we fixed the satisfy, the digit, letter, character, that's all compiles automatically, because we implemented that using the satisfy function. Many we have to fix. Let me just check, because that's tricky. Right. So in order to do that, I first need to fix this combine. Right. So that's already right? Because I wrote it in, yes.
Yeah.
So this is funny enough, it already compiles, but now it's in a different monad. I mean, now we are in lists, but it's also a monad, and it's just true. So it's just the interpretation is different. In the maybe monad that we wrote the combine before, it said, okay, apply the first parser, and if that fails, the whole thing fails, and if it succeeds, apply the second parser to the remaining input. Now it's in the list monad, but it basically says the same thing, only that, so apply the first parser, and then that's indeterminate. There may be several possibilities, so let t be one of the possibilities, and apply the second parser to it. So it's quite cool that automatically already succeeds. And now let me see the many. Right. So many. So So what are the possible unconsumed inputs? So many could mean we don't apply P at all. So then the whole string is the combining input, remaining input. So that's the first solution. And then we can just recursively apply P once and combine it with recursively many P. So either we don't apply S at all, or we apply it at least once and then recursively many times afterwards. And this is already good. And now this end of file, okay. So in this case, it succeeds, and the only remaining output is the empty string, and in this case, it fails. And this is relatively cool that I had to change so little to switch between the implementations, which is because most of the stuff I did was defined in terms of these primitives, so I only had to change the satisfy, and then it works. And now we can see, I mean, first we can try whether the old stuff still works. No, we can't, because I lost my history. But what was this problematic example we had? I mean, okay, let's first do something simple like many digit. 1, 2, 3, x, y, z. This now gives us all possibilities of unconsumed input. So we could not consume any input at all, so the whole string is left, or we could consume the 1, or the 1 and the 2, or the 1, the 2, and the 3. And right. And now this problematic example was, what was it? Many letter combined with the character A. Applied to whatever, I forgot, A, some more letters. And now it succeeds, and it picks exactly the right amount of letters for the many, so that it can then consume the A, and then the JK789 is left. So in this case, there's only one solution, basically, because there's only one A. If I had two A's in this thing, then it should find both of them. Yes. So it can either consume the G and, I mean, the many letter can either be the G and H, and then it consumes the A, or the many letter can consume the first 4 and then consumes the A. So that seems to work nicely. And let's just see. Yeah, it works. Right, and now we can actually, once we have this, we can define another nice combinator. So we had this combine to do parsing in sequence. And we can also do like alternatives to choose between parsers. So choose, parser, parser, parser. So the idea is one or the other, which corresponds to like having different productions for one non-terminal. PQS, and that's very simple. So we can, all the solutions of trying P combined with all the solutions of trying Q. So now, for example, we could have letter choose digit. And that would now succeed both for something that starts with a digit and something that starts with a letter, but fail if it starts with neither of the two. And of course, we can now make it more complicated and, for example, say many letter or digit and have some arbitrary mixture of letters and digits, and it will now do this correctly. Okay. Let's see what else is there. Right. So almost there. Very far. Right. So are there any questions at this point? So now we can like do things in sequence. So we can say, to come back to this, until now we could only do like one line. I mean, what we could do now was, in principle, okay, say it needs a square bracket, in white space, closing bracket. But we couldn't do that. It could also have a square bracket value and square bracket. But now with this choose, we could also have that. I mean, you can say, okay, first a square bracket, then white space choose value, or choose white space value, and then a closing bracket. And probably we could also do these things because we have the many already.
Yeah, we could actually implement.
So I think we could in principle implement this now. So yes. One problem though remains. Normally, I mean, if you have like somebody writes a Haskell program, thousands of lines, and then you like load it into GHC, and then it just says, yup, it's a Haskell program. You wouldn't be happy. I mean, you actually want the program. I mean, you don't just want to know that it belongs to the language. That's all very well, but actually you want the syntax tree. I mean, the abstract syntax tree. You don't just want to yes or no. You want the thing, and that's what we do next. But I think we should have a break first. Questions?
Just a general question. So, if once you have passed the text file, right?
Mm-hmm.
What you get is not, in this case, you're just printing them out, right? But we build a syntax tree.
Mm-hmm.
So is that what is the next step if was to build a programming language, a simple one? Would I take that syntax tree and build a compiler for it?
Yes. So normally compilers take the syntax tree as input and then produce assembly or something.
And at the assembly part, is it something that they normally take that's already there, or is there another step to match assembly language with syntax tree?
I mean, that is basically the point of building a compiler. I mean, so the point is the compiler writing doesn't, I mean, it's normally you first have a parser to give you an abstract syntax tree, and then there are like 10, 20,000 books on compilers. I mean, how to actually write a compiler for your language. I mean, that's a completely different topic. Now it's just about getting from a textured representation to like this syntax tree, that you know it's a valid program, and yeah. And we are only talking about that part, not about writing compilers, even though we will have examples in some exercises where you do actually write, maybe not a compiler, but an interpreter. So for simple languages that you can like write an interpreter. So you first parse it and then you interpret it. Yes. Okay, other questions? Okay, then let's have a short break. parsing but doesn't give us the actual syntax tree, which is not very useful. So now the fourth idea is to add the syntax tree to these results. So parser for a type A takes a string and then gives back all possibilities to parse an A, and it gives you the remaining input. So this is now the idea. So now it will give us a result, not just say yes or no of type A. And for technical reasons, I changed that into a new type so that we can later give type class instance for this. So let's call it parser. And I often need access to the actual function, so I use this syntax. Right. Okay, and now I must, of course, change my stuff. So satisfy, I mean, I must say what the result type is. In this case, the result is a character. So, so here I must just not just return the remaining input, but also the character I've actually passed. And of course, I must say, sorry, now of course this, it's, I mean, but it must be a pass. Hang on, let me just comment this, otherwise I don't see the errors, because there are so many syntax errors now, or because the parser is missing the argument. No, I mean, it must be of type, sorry, do this slowly. Parser, so given a string, so if the string, I mean, as before, if the string is empty, then it's the empty list. And if it's not empty, then like why is not everything? Okay, that's annoying.
Yeah.
Can I disable that?
Maybe you can disable the hint.
Yes.
Try to ignore.
Yeah. Okay. Okay. So that's the same as before. The only difference is, I mean, now because the type is different, I need the constructor, the new type constructor, and because now I don't just return the remaining input, but also the actual value I've passed, I must add this C here. But the rest is exactly as before.
You have an error in the...
Yes, I have an error there. Oh, because I didn't give it a name. Because, yeah. Okay. Right. And now hopefully, okay, let's see. Let me first. So, okay, so now digit is a parser character, then that just, so the nice thing is that most of our code still works. Okay, so many, so what, maybe I should put this, I mean, this is very fundamental, that could go right to the top actually. So this doesn't pass anything useful, I mean, either we are at the end of file or not, but now I must add this result, the unit result here. And of course, sorry, I mean, because it's, so it's a parser, and Okay, satisfy digit, letter, character. Right, before I get to these, let's look at this. So this is a bit annoying. I mean, I had to give it this type because I'm using satisfy. And satisfy, I mean, results in a parser for a character. But actually, this is like useless because the char parser passes for a specific, looks for a specific character. So for example, char plus would only succeed if the string starts with a plus. And now it would give me as a result this plus, but that's like redundant because I know if it succeeds, it must be plus. So it would make more sense to have a unit here, but then of course it's not type correct anymore because satisfy gives me a character, a parser character. So we want to be able to somehow change the result type. I want to be able to just forget the C. Let me just fix this. So what we can do is we just make our parser type an instance of functor. I could derive that automatically, but just for practice of these type classes, let's do it by hand. So functor parser, where? Okay, I need fmap. And so in this case, type signature is A to B, should help me to turn a parser for A's into a parser for B's. And I need to do this, whatever, F, P, parser. Let me just fix this, because I need this in order to give the signature. No. Need this extension. What is that? I saw that before. Oh.
Yeah, I think that's
yeah, okay. H-lint. Yeah, okay. No. Why? Oh, sorry, just. Okay. So this is just because I didn't want this hint. So anyway, so not important. Right. Okay, so how do I do that? So I given the string. I can do it in the list monad, but I can also, for variety's sake, I can do list comprehension. So what do? I mean, I first run the given parser, the P, and that will give me a list of tuples A and string. So A, T, if I run the given parser P on S. And now but I want a list of tuples of type B, T. So the obvious thing to do is to apply the function f to the results, and the unconsumed input is the same. So maybe before we proceed, I can just like demonstrate that. So now let's first, whatever, run. Now I always need this run parser, letter, A78 or whatever, so that succeeds. There's only one way to pass a letter. The letter I passed is A, and the remaining input is 78. So far, so good. And now this functor instance, so for example, I can now fmap, if I import data.character, I can now fmap, for example, to upper over this parser, because now it's functor. And I mean, the behavior is the same, it's still one solution, but now it applies the function to all the results. So now it would be a capital A. Okay, and using this, I can now indeed turn this char into a parser unit by just, I mean, I could use void, or I could just say const unit fmap over this. Now it will probably tell me or use void. So this is actually the same. I mean, we saw void before, so maybe I can do that. I mean, we saw that in the context of monads if I'm not interested in the result. So okay, now I can try this. So now if I do run parser, whatever, character A, it will succeed but have forgotten the A because I know it's an A because I'm looking for an A. But if it starts with something else, then it will fail. So as we want. Right, now let me just check the slides. Did this functor, okay? Right, so now let's look at, before we look at many, because in the order to define many, we needed this combine. So first of all, what should the type be? So we have two parsers, one for A's and one for B's. So what should the result type be? I mean, an obvious choice would be A, B. And we pass an A, then we pass a B, so we have a pair of an A and a B. But this is just in practice not nice, because if you have like 5 things in sequence that you pass, you get these deeply nested tuples. And normally you want to combine these results, I mean, these things, the pieces you pass to some like different type. And that's incidentally, even though probably you won't see that, but I mean, in practice, it will turn out to be very useful. This is exactly what applicative is well at. So what we want, or maybe I should, before we talk about applicative, so a better type for this is if we have a parser for a function type, and then a parser for A, we can turn it into a parser for B's. So that may look weird, but it will turn out that it's really useful to do it like this. But it would be equivalent, like logically equivalent, to use the tuples. It's just in practice much more convenient to give it this seemingly weird type. So let's see. So combine P. I think I diverge a little bit from the slides now, but for a second. Okay, so parser, giving a string, what do I do? I mean, it's as before. So I, in the list monad, so I run the first parser and get a result of type function from A to B and some remaining string input by running the first parser on the given input string. Now I run the second parser, which gives me an A on the remaining input string of the first parser. And now I can return pure. Okay, so now I have something of type A to B, and I have something of type A. So I can apply the first to the second to get something of type B. Right. And not sure I can think of a good example. Okay, fine. Just to convince you that it might be useful, that one can actually use it to combine things as before. So we have our digit parser. That's already defined, yes. Right, and let's say we want to now, I mean, as before, we could combine digit with digit to pass 2 digits. But now, if I want to do that again, of course, it wouldn't be type correct because I need a function. But I can use the functor instance to get one. So I can do digit, or let's say letter, doesn't matter, letter. And now I turn that into a function from character to string by taking a C Sorry, just think. Letter. Letter is okay. Letter is a C. Gives me a character. And I can now turn that into a function from character to string by combining the two. And so don't despair, this will be better soon. Okay, this thing. And let's call it P. The type of P is parser of strings. And now if I run this on the string A, B, D, oh yeah, the P, it does what one would hope. So this, of course, was a bit strange how I defined this, but we won't need to in practice. Just to convince you that having this with this weird signature now is enough to actually achieve what we want, that we can still like use our, like if we have a parser for letter, we can turn it into a parser for 2 letters. Right, and this of course is, if you have paid attention about applicative, this is exactly the signature of this app, the star operator in the applicative. So the obvious idea now is to give an applicative instance to our parser type. Then we don't need this combine anymore, then it's just a star. So let's try this. Or we could of course keep the combine and use it, but let me not keep it. Let me. Okay, instance applicative parser where? So we need the pure. We worry about that soon, but the app we have. So, and that's exactly this type of combine. So we have the implementation here already. Right. So now what about pure? So I mean, if you think of what I said about monads, what pure means, it's normally it means it's just a pure result without side effects. So now, of course, the question is, what is the side effect in the case of a parser? And the side effect in parsing is to consume input. So pure A would be, it just passes an A without consuming any input. So that's, and how do we spell that? So it's parser that given an input string S returns, passes an A successfully and doesn't consume the input. So it's still the whole string. Right, now we have an applicative instance. And the nice thing is that with this, we have a slew of useful things from applicative, but we look at them in a second. I think first we do, for example, we automatically have, no we don't, okay, let me see, that was here. So applicative did this. Right, so now we have like things that are defined in control applicative. We haven't seen them before, I think, but and there are lots of them, but they are all quite suggestive. So it always means, we have seen this with brackets, angular brackets on both sides, and this is the star operator with angular brackets on both sides. And basically the mnemonic is, if you have the bracket missing on one side, you ignore the result there. So for example, this one here, parser A, parser B, it passes an A and passes a B, but it ignores the B and just returns the A. And here the other way around. It passes an A and it passes a B, but then it ignores the A and just returns the result of the second thing. So, and this, given an A and parser B, it passes the B, but forgets the B and just returns the A. And so that we now automatically have, because that's just, we have these operators for all applicatives. So for example, one example is on the slides. We can, now that we have that, rewrite our character if we want, like so. And yeah, now it complains again, and I, yes, fine. Just as in maybe void, I mean, it's a matter of taste, what is easier. So this means, I mean, pass the string according to the right-hand side, but then ignore the result and just return as result this. And I don't know, for example, we could do something like, to demonstrate the others, for example, run parser, let me, yeah, fine. Run parser, for example, character plus, and now we ignore this and then letter. And now we need a plus in the beginning and then a letter and whatever. And it will just pass the letter and ignore the plus. So this is now, because I use this whatever it's pronounced, the star arrow thing. So I need the plus. If it doesn't start with a plus, then it will fail. But then it throws away the result of that parser. It just makes sure that it could pass that. And whatever, the other one, I mean, of course, I can do it the other way around. So if I use this one, so now it says it, I mean, it starts with a plus, and now there must be a letter, but the letter will be ignored. So I just get the result of char plus, and that was always unit. I don't get the R now. And that is useful, I mean, if you know sort of like this, whatever, a semicolon or this square bracket. You don't need the square bracket in the result somehow, you know it's supposed to be a square bracket, but you need to pass it. It must be there for it to be valid, but you are not interested in the result. So this is extremely useful, these operators. And we now have all of them for free because we made it an instance of applicative. And of course, now we can do stuff like, I mean, with applicative syntax. So what was so horrible before, when I try to do two letters, I mean, I can now do that much nicer with applicative syntax. For example, I can do function taking two characters and mapping them to the list containing them. And now this usual applicative syntax, how we motivated it, letter, star letter. And this will now pass two letters. The first, I mean, pass letter, pass one letter, pass two letters, and combine the results with the given function, which in this case just puts them into a list with those two characters. Which means in particular, if I did this here, then I would get this original version back that combine could have gotten type parser A to parser B to parser A, comma B, which shows that this version, the star version with the weird signature, is as powerful as if I had returned the tuple. But it's actually more, so I haven't lost anything, but I gain all these niceties that it's actually much nicer than to work with it. So that's also a nice exercise to basically show that if you have a function FA to FB to FA, comma B, that's basically equivalent to applicative. So one could have defined the applicative class like this, and this is more or less the proof. Anyway, at least in one direction. But that's just on the side. So we have this. Right, and now let's see what's still missing. Okay, so we have this combine taken care of while implementing applicative. now there is still this choice thing. And we could implement that, but there's actually now a type class that's important and that we haven't talked about yet, and I have no idea whether that's in scope. No, it's not. Is that in control applicative?
Yeah.
So let's import control applicative. Let's try this. And that is called alternative, the class. And we see it has two things that we need to implement, empty and this thing. So this thing is what we have called choose until now. I mean, the class is called alternative. I mean, basically this means you have like two alternatives. And empty is something like failure. So you fail. And that's the unit for, so if you do empty choice something, then that doesn't do anything because empty failed, so you end up with this. Anyway, so let's first do the whatever empty. Sorry. And we see that there are lots of instances, in particular lists and maybe an instance of alternative. We talk about that a little bit more later, but let's do this now. So instance alternative parser. Where? So we have this empty. So that must be a parser for everything, which already shows, I mean, after what we said in last week, beginning like about undefined and so on, it already gives a hint that it must be some sort of failure case, because I obviously can't produce a result A ever for any possible A, because I don't know anything about A. So if I want to implement that, it must be some sort of failure, like so it must be of type parser A. The F was stupid, of course, sorry. Right, so that's the parser that given a string just fails. So I can say const the empty list. It has no results. That's the parser, empty is the parser that always fails, no matter what input string I give it. And now the interesting one is this operator. So given a parser A and another parser A, I basically want to try both of them. That's, I mean, earlier it's our choose. So if I have P choose Q, so it's a parser given S, and it's basically the implementation is exactly as before. I just run the parser P on the input string, and I concatenate all the results with running the parser Q on the input string. So this is now our choose. So if I reload, so now I can do this letter or digit. So run parser letter or digit on whatever x7 that succeeds because it's a letter and it passes the x. And if it's instead a digit, it also succeeds and passes the digit. But if it's neither, then it fails. So that's exactly as our choose before. And the cool thing is, by making it an instance of this type class, sorry, we saw that just when I asked for information. We see that part of the type class are already some things called sum and many of this type. So we don't need to do our star explicitly. That's already automatically once you have alternative. So that means our things become simpler again. So I can get rid of all of this, and I just have it now. So we can try it. So for example, run parser many digit. So this is as before or many, so it passes, it consumes 4 digits, 3, 2, 1, or none. And sum is at least 1. So if I do sum digit, it's 1 shorter because you can't, I mean, you must have at least 1 digit. Right. So now basically we have everything we had before, but now with results. Did I forget anything? No. Cool. Let's check the slides. Right, and another thing that's built into applicate alternative or is in the library. So once you have alternative, you have optional automatically. So let's try it. Run parser. Optional digit, for example. So if I have 1, 2, 3, so it can pass. I mean, there's a digit, the 1, just 1, or it cannot pass it, and then it's nothing and doesn't consume anything. And actually, with this, maybe I think that's not in the slides, but maybe we should now use that to implement, for example, from the slides there was this natural numbers or ints, so we can now we have enough to pass that. And okay, so one problem is, I mean, our digit thing is a character, but actually we would like it to be like a natural number. So this is now an example that's not on the slides, but I think it's useful to do this now. So let me import numeric natural. And I don't want to mess with the type, so let me just define digit prime or something, which is a parser natural. And I just fmap something over digit. So I just need a way now to convert, let's just call it f. So I need a function that takes a character of which I know it's a digit character, so it's 0, 1 to 9, and actually turns it into a number. And I always, I mean, it's some like ASCII encoding. So, I mean, one way to do, I mean, of course, I could just give 10 equations for each possible digit. But I'm lazy, so I don't want to, so I use this from enum and just checking. So the ASCII of 0 is 48, and the one of 9 is 57. So I can just do this by doing this from enum C and subtracting 48. Why does that not work? What's the problem? Oh yeah, I must convert it to a natural, right? Okay. So if I try this now, so run parser digit prime on whatever 7 CV, then now I get an actual 7. I mean the number 7, not the character 7. Right, and actually I should have given this a name because I need it for non-zero digits as well. Do I? Actually, yeah, maybe. So let's call it car to nut or something. Okay, and now I also need this non-zero digit because natural numbers are not supposed to start with a. So let's turn that into a parser natural immediately. So we start with satisfy lm so no zero, and now again our character to nut. Okay. So if we remember, so what's the natural number? I mean, maybe I should show the slides again. I want to now, as an example, show you like a. We could also do this stupid type, this DNS, and we will. But I mean, I think naturals are more interesting. Right there. So we said a natural is either 0 or it's a non-zero digit followed by one or many naturals. So now we can implement that. So let's call it, I don't know, natural. So a parser for natural numbers. Okay, and we can just follow the two cases. And now we also can see some of these operators in action. So the first case is just the digit 0. But if I write character 0, then that's not type correct because this is a unit, but I need a natural. And that's where this bracket $ is for, that we saw before. So I can just say this. So this means pass the digit 0, but then return as result the natural number 0. Ignore the result of what you passed and just return the 0. So that's the one case. And the other case is, so alternatively, it can start with a non-zero digit, and then, so that's not correct yet because I somehow have to assemble them. So I need something here. And then 0 or more arbitrary digits. And I use my digit prime now. Okay, so this is, I mean, I come to the underscore in a second, but that's exactly what it said on the slides. So it's a 0, the character 0, or it's a non-zero digit followed by 0 or more digits. And I more or less directly translated that into code now. So the first line is the character 0, and the second line is non-zero digit, and then 0 or more digits. So the only thing is now, I mean, this is just like whether it's correct or not, I must now produce the actual natural number. So there, what's missing now here, so now I get a non-zero digit and a list of digits. And now I must somehow assemble that to a natural number. So let's, I mean, this is more like, so I have a natural number that's my non-zero digit, and I have a list of natural numbers, but it's all like single digits, and I must assemble that to a natural number. And I mean, I don't want to dwell on that too much. So I mean, this is just, if it's empty, the XS, then it's N. It's N. And if it's not empty, I mean, this is now primary school stuff. How does our number system work? I mean, if you have a 1 and a 2 and a 3, how does that relate to 123? And you can do this if you want, like 10 times n plus x. I could also do it with fold left prime. Maybe I should. Maybe I should. Maybe I should. Fn equals fold left prime. I always forgot what.
First the function and then the accumulator.
Yes, first the function. So given the accumulator and the next digit, right. So given the accumulator and the next digit, I multiply the accumulator by 10 and add the digit. And the first value of the accumulator is the n. And that is, I can beta. Why doesn't it work? because I must import it. Right. So I mean, this has nothing to do with Haskell or parsing. This is just how does a string of digits translate into a number. I mean, you take the first digit, and then if there's more, then you multiply what you already have by 10 and add the next one. Right, and now let's see. Run parser natural. So let's start with 0, for example. So that works, so I have 0 and 7. Yes, so that all works. But if I, for example, have 0, 2, then it must be 0 because I don't allow a leading 0 if it's not 0. Okay, and now using that, the next slide was we have this sign, and then integer is is an optional sign and a natural number. Okay, so now we can basically verbatim write parsers for that. That's why parser combinators are so nice. It very closely resembles the structure of these rules. So basically you can just read off the rules and write the parser for them. So now that's int, so maybe first sign, but that's, yeah, maybe I do that because I do that like with a where clause. So I tried whether I should, I mean I can be evil now and do the sign as a parser of a function from natural to integer. So let's first worry about the sign. I mean, the question is what should the result type be? I mean, for example, we could say character, so we get a plus or a minus, or we could say bool, we get true and false. But I mean, what we actually want is I mean, if it's a plus, I mean, we pass the natural number. If it's a plus, that's just it. And if it's a minus, we want to negate the natural number. So therefore, I think it makes sense to pass it as a function from natural to integer. So there are two cases, plus and minus. So so it's either plus, in which case it's just the function is just from int or to integer. Character plus, or alternatively, it's negate after to integer with character minus. Okay, and now we can, so what I mean, we do something and then we pass an option, no, sorry, that was, no, here now. So we do something and then we pass an optional sign and then we pass a natural number. So that's our integer. So what do we need to do here? So we get an optional sign, so maybe natural to integer, and a natural, and we want an integer in the end. So if we don't get the sign, then it's just to integer. And if we do get a sign, then it's this function. Right. Okay, and now we can try this out. And why is it complaining? Because it doesn't have a signature. So now we should be able to pass integers as well, both with sign or without sign, so with optional sign. So let's see, run parser integer. So let's first try without sign. Okay, that works, and the 0 works, and now some other natural number. It works, and if we want, I mean, this always gives us all these options. If we want that the whole thing is an integer, then we can use our end of file. So now, I mean, the whole thing is an integer. It's an integer 1863. And now we can try optional signs. So plus works, and the minus also works. But if there's something else or something weird, it doesn't. So yeah, so that's a parser for integers. Although, I mean, of course, it's maybe debatable whether something like +0 or -0 should count, but it does with our grammar. I mean, why not? And I mean, plus 17 or so is also a bit weird, but also doesn't do any harm. One could also have said it's, I mean, instead, I mean, one could have said it's only an optional minus, not an optional plus or minus. Right, are there any questions at this point? So now we can pass numbers, at least integers. Okay. Maybe we can revisit our, this other example we had, this running example, this here. So now we can write a parser for this. And in principle, the beauty is that now we can, in principle, it's completely mechanical. So we can just take this definition and we could basically automatically generate a parser for it, more or less. Not really, because we need to know the terminals. But it's very simple, so I think it's instructive to write parsers for this. So we need, but of course I can't because it's in another module, but that's fine. We don't despair. We just import parser 4. So here's our example with our evaluate our semantic functions and so on. So let's write a parser. And again, it's the same as for the semantic functions. We basically need a parser for Ds and for S's, and they will sort of call each other. So parser for S, or parser S.
It's already a parser.
No?
No, sorry.
That's fine. So parser for S, and we want a parser for Ds. So let's start with the parser for Ds, because D is very simple. It has two constructors. So the constructors will correspond to choices, to alternative. So we need like two choices. And now that, I mean, okay, so 0 would be if we pass a character 0. So that is character 0. But, I mean, the result should be of type D. So this is another example how to, when this thing is useful. So we pass the character 0, but then the result is the capital 0 value of type D. Or alternatively, character 1. Right. And now for S, so we have two cases again, so it will again be two lines alternatives. And okay, the first case, D plus S, so we must pass a D, a plus, and an S, and then apply the plus constructor to the D and the S. And the plus must be there, but we don't need it to construct the value. So this is plus, alternative syntax. So what was it? D. So we pass a D. Then the plus, but we ignore it. Character plus. Something weird got. And so So for example, I could write like this. I never know about the parenthesizing of these things. And now parser S. And let me just remove this stupid thing. Okay, so this is basically literally just written this D plus S. So I pass a D, I pass a plus, I pass an S, and then I apply the plus constructor to the 2. Why do I get an error here? Oh, because here something is weird. I hope. If I put parentheses around that. Okay, fine. I should probably.
Export from there.
Yeah, maybe not. Let's not get fancy. I wanted to, but because I don't have an explicit import list, then I would first need an explicit export list. So let's just do a control applicative here as well. So, okay, and that was the first line, and now the second one. Alternatively, an S could also be a D. So that's the digit constructor, and then just parser D. And now we should be able to, hopefully, okay, run parser, parser S. What was our example? 1 plus 0 plus 1. And now it passes this. Oh, okay. And they have different ways because I didn't have an end of file. So if I do this, then we get exactly, I think that was our example 1. So the 1 plus 0 plus 1 is now passed. So now we have the abstract syntax tree. So I think this is absolutely beautiful how, I mean, we have this correspondence between grammars and Haskell algebraic data types, and then the algebraic data type very closely, is reflected in how we write a parser for it. So basically, it's almost effortless to write a parser for these things once you have all the machinery. And that's this combinator, parser combinators. And we saw that, I mean, yeah, this is, of course, a stupid type, but as we saw with the parser for natural numbers and integers, it's actually useful. I mean, that's what you would need if you wanted to design your own programming language. Then it probably want arithmetic in there and numbers. So you would need something like that as building blocks that you can parse numbers. I mean, of course, this is now just integers. You would need something for floating points or decimals as well, but obviously that's not very difficult. I mean, now we could say if it can have a dot afterwards, and then could do that as homework. Right. Just checking on the slides. Sorry, too far. Okay, this I already did. Maybe I do the 5th step as well, and then we have another break. Or is it too early? But then that's basically the first lecture here. Yeah.
Maybe we can do the first things or the second.
Yeah, we can. Right. So are there any questions at this point? So now that was the biggest step from step 3 to 4. Now there's a last step, but that's basically just technical. So let me copy once more from 4 to 5 and change this here. And close this, close this. Name it. Okay, so the only other thing is that right now we are, I mean, specific for strings. And I think in previous iterations of the course, this parsing lecture was further away, I mean, later in the course. And there was a lecture before about common data types in Haskell. So there's a lecture where I talk about string types. So the point with strings in Haskell is it's very nice to work with because it's just a list of characters and there are millions of functions working on lists. So once you understand lists, you automatically understand strings. But they are a horrible choice for like large amounts of text because of the way, I mean, which we will also see in that lecture, lists are implemented. There you need like, I forgot, but something like 16 bytes per character on average, or 8 or something. But far too much, so it's like very inefficient. And in Haskell, there are like better types. And first of all, there's so-called byte string type, which is just like bytes. And secondly, there's something called text, which is just for Unicode text, but like string, but it's much more compact representation. So if you deal with like large bodies of text, you wouldn't use string. Plus, I mean, we talked about lexers before, so maybe before you pass your programming language, you first tokenize it with a lexer, and then you don't have characters or anything, you just have some tokens, whatever, keyword, number, operator, and so on. So it makes sense to not just be able to pass strings, but lists of an arbitrary token type. For example, if you could do that, then these byte strings is just lists of bytes, basically, then you can also pass binary files, not just text files. But that doesn't make it more complicated or anything. It's just a small generalization to go from string to lists of arbitrary stuff. So we basically add a second type parameter here, the type of tokens, which in our example was always character. So we just abstract from string to list of tokens. So everywhere where we had string, we just write list of tokens. So then parser t now is a functor. And everywhere I have to put the t. And parser t is an applicative. Parser t, t, t. Parser t is an alternative. T, 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 end of file. So this is now parser TT, and character is T. Digit doesn't make sense for other T's, so let me keep that as a specialized to character. Now this character we can generalize to arbitrary tokens, so it just passes a specific token. So we can rename it to token. And the only problem now is that this here will complain. It doesn't because of other errors. But this was my example anyway. I can delete this here, I think. That was just the example. Or I can leave it and comment it for the time being. Yeah, it's useful. Let me not delete it. I just fix it. I mean, the problem, of course, is that for arbitrary token types, if you don't know anything about the token type, it's not necessarily an instance of eq. So this only works if I have eq t. Right, and now I can like recover my examples, hopefully. So this is now all specialized to character. Okay, and char I don't have, so that's now token. Okay, so now this compiles again.
No.
No?
There's an error. You can see it in the right.
Okay, yes.
You can click there. No, on the minimap.
Oh, not this
Yeah.
one as well?
No? Oh, token.
Okay. Oh, I haven't saved. Okay. And now if we want, we can go back to this example and just, instead of parser 4, import parser 5 and change the types to character. And then we have to say token here. And that should fix that. So yes, so that's the last thing. So now we could also write parsers for things other than strings. I mean, as I said, like binary formats. Now you could parse whatever, MP4 or I don't know of a good example. I mean, for example, bits. I mean, for example, we could write, I mean, if we represent bits as booleans, then we could write a parser for that parses a string of bits as a natural number, for example. So we could write whatever, let's call it binary. It's a parser where the token type now is Boolean, and it gives me a natural number. Not very interesting. So, and actually I wouldn't need a parser for that, because it's just, because everything is a natural number. I mean, except maybe I could, of course, have the leading zeros, that it must start, that it must be a zero, I mean, false, or that it mustn't start with more than, no, not sign, I mean, that it mustn't be 0001 or something.
Right.
Maybe to make it a little bit more interesting. Otherwise, every bit string would be valid. Okay, so, I mean, it's basically the same as I did before, just binary now. So I can say, okay, either it's the token false, in which case it's 0, or it's the token true, it starts with a 1, and then 0 or more tokens that can be true or false, or satisfy const true, arbitrary bits, and then I must somehow, hang on, and this, I could ignore, I mean, yeah, okay, fine. So this doesn't give me an interesting result anyway. And now I need something here. And what is the problem? What seems to be the problem here? Okay. I must somehow maybe bracket this. Right. And now I need to fill this in. So now I get a list of bits and that's basically the same I did before. As I said, only in binary. So now it's from list of bool to natural, and I have the leading one, which I don't get explicitly here. So it's again so it's again fold left prime, given the accumulator and the next Boolean digit. So if it's definitely 2 times the accumulator, but if B, then 1 is 0, and it starts with 1. That's the leading one. Okay, and now now I can try this. So if I have, for example, and with end of file, so I
need to apply it.
yes. So if it's just empty, it fails. If it's just the digit, just the off bit, it's 0. If it starts with an off bit otherwise, it fails. So it must start with a 1. But now we have 1, 2, 3, 4, and so on. And okay, so this, and now I represented bits as booleans, but this would now be a parser for a bit stream. And I could also write one for a byte stream and do whatever, a binary format. Just as an example, why it might be useful to not just support string, but arbitrary token types. Are there any questions here? Yeah?
Number one, could you kindly just break down the full notation you put?
For the binary or for the fold L? Okay. Let's see. I know it always starts with a 1 because I'm in that case. So I pass this token true, but I'm ignoring it. So I don't get the leading one, I only get the others. So I always have something like whatever, 1, 0, 1, 1, 0, 1. So what I do is, so it's 1 times 2 plus 0. Oh, let me write it how I wrote it. So you can start with the leading one, you multiply it by 2 and 0, it's 2. Times 2 is 4, plus 1 is 5, times 2 is 10, plus 1 is 11, times 2 is 22, plus 0 is 22, times 2 is 44, plus 1 is 45. So if I'm not mistaken, that's 45. 1 plus 4 is 5, plus 8 is, probably I made a mistake somewhere. Let's see. First of all, let me see whether this is correct before we discuss further. Sorry, just 1 second. How can I do this? Can I do this? Okay, 45, fine. But is this 45? 1 plus no 2, 1 4 is 5, 1 8 is 13. Yeah, no 16, 1 32. It's 45. Yes. So I start at the left, and each time you must, if you have, it's the same what I did before for in decimal. You have something, some number, and you have passed to, so you have 237. Now to get to 2378, you have to multiply this by 10 and add 8. And in binary, it's the same thing.
And you can parse it actually now to demonstrate.
Oh yeah, that's right. Except that I used ones and zeros, but I can run parser binary. binary end of file. So true, false, true, true, false, true. And it's 45, yes. Nice. Right. Other questions? Okay, then maybe I go to Monad Plus and then we have a break and discuss what to do next. I mean, I do Monad Plus still, the Monad stuff, and then,
Okay.
or not? Do you think we should have a break now?
Maybe a break now.
Yeah?
Maybe it's a lot.
Yeah, I'm happy to have a break. Should we have a break now?
Want to have a break or let's keep going? Break?
Okay. the parser for B's. Right. P continuation. Okay. It's a parser. Given an input string, what do I do? I'm in the list monad. So as before, first I run the first parser and get an A and pick an A and the remaining string. So now in order to get the second parser, I have my continuation that I can apply. So this is now a parser B that I can run. Applied to the input string T. And that's it. And now that I have the monad instance, as we learned before, I don't need this app anymore explicitly. This is just defined in terms of this monad app. Once I have the bind, I get right. So that's that. And we could write an example, to use do notation. I don't really know a good example, but one example might be, now that we have a parser for integer, to turn it into a parser for int. So int parser character int. So we could just start by passing it as an integer. And now we just want to check whether it's in the bounds. So if n is greater than min bound. Okay, let me first maybe call it min b. Max b.
I think with one is enough.
I'm sorry?
With just the min b, it's enough. I think the other one can speed up.
Let's see. Of course, now at the right hand side is an int, so I must do 2 integer. And n is less than or equal to integer max b. Then I can just convert it to an int. So I can do a pure from integral n. And otherwise it's too large, so I fail. How do I fail? For example, with empty. That's the failing parser. So we can try this out. Run parser int. I don't know how big I can go.
Maybe that's enough.
Yeah, that's probably enough. So, yes, it is enough.
It's 5.
It's more than enough. So we see that it starts passing like 1 digit as an int, 2 digits, and so on, until here. So that's still an int, but it can't consume the next 2 because then it would be out of bound. So yeah. Right. Just an example how you might want to. Where it might make sense to use do notation for parser. Okay, and then there is a class we haven't seen yet. Not sure that's in scope. No, that in control monad.
Yes. I thought we already have control mode.
But only up.
Oh, okay.
Right. So there's one class that we haven't seen yet, but don't fear, that's very simple now. So there's a class called monad plus, and it has as superclasses alternative and monad. But it's basically the same as alternative. So M0 is like empty and M plus is like whatever that's called. So it's just like the version for monad, but it's the same functionality. So I can just implement it by defining M0 as empty and M plus as this operator. So that doesn't give us any new power or anything. It just signals that it's in particular a monad. So instance monad plus parser t, where M0 is empty and M plus is this M plus. Okay. So that's basically nothing new, but there's just this, I mean, this type class exists. So that's for monads. But it's the same functionality as alternative. Right. And okay, and these classes are also, this monad plus is, or alternative actually, is not only interesting in the context of parsers, that can also be interesting in other contexts. And we saw earlier that, for example, list or alternative, list or maybe are instances. And maybe go back here. And just as an example, so that has now nothing to do with parsing. So let's say we have a person type, just whatever name. And I don't know, cell phone. And work phone. Or home phone, whatever. Or landline. What did I do?
This may be string, I think. The phone.
Oh, there I forgot the constructor again. Right. Let's say we have this type. Just an example. And now we want to, whatever, person phone. So the idea is we want a cell phone, but if he doesn't, sorry. And this is optional. So maybe he doesn't have a cell phone, or maybe he doesn't have a landline. And now we want something from person to string, which looks up a phone number, but we would prefer a cell phone number, but if he doesn't have one, we want to take the landline. So we could, of course, implement that by hand. So we can say person phone P, case cell phone P of nothing. Then we try the landline. But if it has, then we give this and what, or maybe string. Right. And so if we have whatever, person phone, last, I don't know. Okay.
Have to reload.
Now I have to. No. Why not? What, didn't I? Oh, I'm in the wrong module. Okay. So it would find the cell phone, and if I have a landline, it would still give the cell phone, but if I don't have a cell phone, it would instead pick the landline. But if I have neither, then of course the poor function also can't do anything about it. Okay, but you could now, because maybe it's an instance of alternative, one could much more concisely write it like so. So the alternative instance of maybe is exactly like this. If the first one is a just, it gives that, and if the first one is a nothing, it gives the second one. So if I reload and should still do exactly the same as before, right? So this can often be useful for other situations as well. Just trying to, yeah. Okay, so that's this alternative. So that's not just for a parser, but it's normally some sort of choice if you have several options as well. And for list, it's just concatenation. So, we had this concatenation, but the alternative instance for list is just this. I don't know what for I/O they also had it. I have no idea what it is for I/O. I can try it. Maybe just doing both, or if the first one has an exception, or okay.
So if you try to crash the just try that IO error.
It's not an error. It must be int. No, if it's int, it's an error. Diff. No idea what the alternative instance is. Maybe it just ignores it, or I don't know. Anyway, I never used it anyway. But yeah, so that can be useful in other contexts than parsing this alternative class. Okay, so that's, I think, right. The slides, so we finished this lecture, the first one, but there are actually 2 lectures on parsing. So I did now the first part of the second one as well. Which is about, just a recap of alternative of what the first one did, first lecture, and then this example with alternative. And lists, and then, guard as should still do. There's one useful thing that you have once you have alternative. That's this, it's called guard. So once you have alternative, you have something from bool to f unit. So for false, it's empty, which basically corresponds to failure. And for true, it's pure unit. And this is actually exactly what in my example yesterday of the send more money, what I called check, that had exactly the same type. So I was basically reinventing the alternative instance for lists because I was in the list monad. So now I could just have said guard instead of defining this check. So this is, if you are in a monad that can fail, I think probably the point of I/O is just that it fails. I don't know. no idea. Then with guard, you can basically stop execution. So, so to rewrite using this, to revisit my example with int, to go back here, int, so I could rewrite that as follows: guard, it must be in these bounds, and then just continue with why does it? Okay. Right. So guard basic, I mean, if the guard is true, then nothing happens and just proceeds. If it's false, then it fails, whatever that means in the context. In the case of parser, it means it fails. Right, so that's very useful often. What else? Yeah, so this would be another way to implement the filter function. If you want to write it monetically, you could just say you pick an X from the input list, you guard that the predicate holds, and then you return a pure X. So that would be a way to, in do notation, implement filter, the usual filter for lists. Okay, then monad plus we did. Okay, we implemented that. Right. So yeah, we did the first chapter of this lecture, and now it's maybe, I don't know, maybe I should mention this. So there's one, I mean, these parser combinators are wonderful. There's just one problem. Sometimes if the grammars have a particular property, so I mean, this was our example. And if the example is slightly different, if you look, so all I did there is instead of d plus s, now it's s minus d. And and if you now follow the same process and write a parser for this, I mean, as I did before, so where before in the first line there, we had parse d plus parse s, now we have parse s minus parse d. And if you then try to parse something, then it loops forever. And the reason is because it's basically, I mean, you can see the loop. So, I mean, the way parsers work, it will first try the first alternative. So it will first try this, but this is itself. So it will forever try to parse an S without making any progress. And something like that is called a left recursive grammar. So you can also see it in the grammar. Left recursive if the non-terminal you have on the left is the first thing that appears on the right of a production. Then you get into that situation. But the good news is that there is a way to modify the grammar without changing the language so that it's not left recursive anymore. But I think I don't want to go into this. So, I mean, you will get the slides. And there is basically the way how you can introduce a new non-terminal and shift stuff around a bit, and then you can fix this. So yeah, so but that can sometimes be a problem. I mean, depending on what grammar you have, if it is left recursive, if you want to use combinator parsing to parse it, then you have to do this transformation first. But I decided that it's not important for this class because, I mean, what are the chances that you want to write a parser? And if you want to, then you can just look it up, how to fix it. And the second thing, I mean, there are some optimizations that you can do. If you have like the same stuff several times, you can basically factor it out. So make your parsers more efficient. Stuff. And then, I'm not sure, I don't want to do this, I think.
It's a bit late.
Yeah, it's a bit late. I just want to mention, so I mean, sometimes you don't care. For example, if you look at this grammar, so an S can either be S semicolon S or it can be a terminal A, let's say. Then that is highly ambiguous. because I mean, if you have 5 A's, basically how you apply this, like 32 or whatever parse trees. But sometimes you don't care, because if this semicolon is like associative, then you don't care about the bracketing. And you can, so maybe you don't care whether it's parsed like this or like that. And in that case, I mean, one can write a combinator that then does that. So you can parse a list of stuff where you don't care about the ordering, how you pair it together. And then you have special versions for, I mean, if you want to parse arithmetic expressions, then it's, it does matter how you bracket it, but by convention, it's left associative. So you can define something called chain L to parse something like that, where it starts on the left, and then, of course, you have something for the right as well. So if it's right associative. And then the final thing here was, I mean, if you want to parse arithmetic expressions, for example, 3 plus 5 times 7, then you run into this problem of operator precedence, that you somehow must treat the plus and the times differently because that binds stronger. And then it's explained on these slides how you can handle that. So there's like a mechanism how you basically introduce different precedence levels and then write parsers for each precedence level, and it's also a mechanical process. So I also think that would be too technical for this class. But if you ever need to implement something like that by hand, I mean, normally there are also helpers for that, then you can just look it up in the slides. And then finally, here there was like a demo of an existing library that's quite popular and basically production ready. And I mean, this is all basically more or less what we learned just now that would just work for this library, and there are some peculiarities. And it's nice, I mean, it gives you like proper error messages. So if you give it a file, a text file, then not only does it fail, it basically points to the position in the text file where it gets an unexpected token. So I mean, this is, and what it expected. So this is again our example, this 01 SD thing. And if you give it a 2, then this would be the output. It would have a caret under the 2 and say expected 0 or 1, but got a 2. And that's basically more or less out of the box. So you don't have to do anything special for that. That just automatically works. Once you, basically you could more or less take the parser as we have it and just use this mega parsec library instead of our own. And then you would automatically get something like that. So if you ever design your own programming language, then you can reach for something like that. And maybe, so yeah, there's some stuff. And lexemes, but it's all, as I said, very technical. And I doubt that any of you will need to like write a serious parser anytime soon.
Next month.
And by then, yes. And maybe the last thing I want to mention regarding parsers is base. That even in the, and there are like dozens of parsing libraries on Hackage with various flavors and advantages and disadvantages. And but I just wanted to go back to the base libraries in Haskell. So what you always have without downloading or installing anything. And there is this, there's actually text parser combinators readp. This is, so it comes with GHT, bundled with GHT. And that is very much like what we just did. So basically, more or less probably, I mean, some of the primitives maybe have different names, like what we called token is more or less this get, except that it does pass the character, so it's a little bit different. So this just consumes one character. It doesn't care which one and gives you that character as a result.
No, gives you the next character.
I'm sorry?
It gives you the next character.
Yeah, it gives you. It could,
Okay, yeah. Sorry.
So it's this would be our satisfy construe. So it accepts any character. And but then basically everything like end of file and satisfy and this one, they made a different choice. So instead of having unit, they do return it, but it's extremely similar. And in principle, basically all, I mean, we did woodwork with this. And it's also, I mean, all the instances that we have. So if we look at this sharp P, I mean, it's a functor, monad, monad plus, applicative, alternative. So that all is basically like that. And I always personally, I mean, for like small things, I mean, not passing a programming language, but just stuff, if you need to pass something, I always use that because it's simple and it's in base and it basically works like exactly like what we just did. Oh yeah, and one last thing I wanted to say to that, read. Remember, we have show class and read class, and we can read stuff. For example, 1, 2, 3 as a int. And if you ask for read, then actually read itself is not even in the class, so that's like a library function. But if you look at that reads prec, it takes some precedence and then returns a read s. And if you ask what is a read s, that is basically our version 4. So this read also is just a parser for a's. So it's not our version 5. It's not specialized to arbitrary tokens. It's specialized. It's not generalized to arbitrary tokens. It's specialized to characters. So under the hood, the read mechanism in Haskell also just uses this parser type. And of course, you can also use this. I mean, so I could. I mean, normally if I do whatever 1, 2, 3 plus plus and read that as an int, it will give an error. It's not an int. But if I use this reads prec, and I must give a precedence, let's say 0, I don't know, doesn't matter. Now list of int, comma, string. Right, interesting. So it gives me one solution. So that it can then also, I mean, for some reason it doesn't give me all solutions, so it's eager. But it does give me like a valid way to pass an int and have something left, like the 2 plus plus. Right, so this is not something exotic. I mean, this is like general, I mean, very common to do parsing like this. Okay, are there any questions? And no, okay. And we could stop. I'm not sure whether the food is already here. Or we could, yeah. So maybe we should stop, except if somebody still has a question. Oh yeah, then maybe just briefly about what happens next. So now we are leaving tomorrow. So that was the last in-person class. And originally we wanted to continue for the next 6 weeks with 3 lectures every week. But seeing as some of you are struggling with the assignments and so on, we thought we could slow it down so that the course in total is a bit longer and we only do like 2 lectures a week if you want, but we don't have to. But now, I mean, we wanted to pack as much, I mean, make use of the time we are here, so we wanted to have lectures every day. But now it doesn't matter. So, I mean, as far as we are concerned, we can also stretch it a bit longer and slow down if you want. So we could do that. Right. And I don't know. I mean, in general, I mean, if we assume the original time frame, then there would be 2 more weeks of Haskell, no, 4 more weeks of Haskell.
2 more weeks of Haskell. Yes.
2.
And 1 of Marlowe.
And the 3.
Of Plutus.
Okay, so 2 more weeks of Haskell, then 1 week Marlowe, this smart contract language for financial contracts. And then 2 weeks, I think, Plutus introduction. And then 1 week where you are supposed to work on your own projects. And if we like slow down a bit, then it would be a bit longer accordingly. Right, so that's the idea. Okay.
Any questions about that? The other guys?
So that's still the plan. 2 more next week will be virtual hosting, right?
Yes, no, but I mean, that's the original plan. I mean, we still have like the same amount of content of Haskell to see, but it will be stretched. Like that's the original plan. Like 2 more weeks of Haskell, 1 of Marlow, and 2 of Bluetooth, and 1 to work. Now all that will be stretched proportionally.
Like slowed down, I mean, 50% longer, like instead, if we do, or whatever it is,
Like, yeah.
instead of 3 lectures, 2 lectures, so you can do the math. I
So
can't.
instead of 2 more weeks, it will be like almost 4 weeks. Stuff like that. Yeah.
Except if somebody like needs to be done with the course in 6 weeks. But if nobody, I think it might be better if you have more time.
To work on everything, ask questions.
And I also don't know, do you plan to like physically meet again or here at some point or?
Probably towards the end when we finish.
Right, right. Yes.
Like if you can have certification.
Yes, yes. Mhm.
Something that has what it's
Right.
Okay, so then there's no restriction to make it longer, right?
No, I mean,
There's no restriction because everyone can like work on home.
Yes, yes.
Yeah.
okay,
Okay, perfect.
good. Then we probably will do that we slow it down a bit and it will take a bit longer accordingly. But then you have more time to work on the assignments and so on, because it's important that you practice.
Yeah.
I mean, you can't learn, as I said in the first lecture, you can't learn a programming language without writing lots of code in it. Right.
Amazing.
Okay, then
That's it.
thank you very much. Thank you
Thank
for
you,
all your
guys.
questions. And
Yeah.
yeah,
Thank you guys.
thank you.